Hello everyone, welcome to this video, which is going to be the paper 2 for January 2013, questions 1 to 6, the first 49 marks. So, what we're going to be covering today is these 6 questions. Let me paint a picture for you. It's the 22nd of January 2013. You were born in 1997 and you're taking your GCSEs this year. It is a bright and sunny exam room and you are doing these 6 questions. Let's have a scout over them. Geometry, trig functions, binomial expansion, looks like infinite binomial expansion. Differentiation should be easy. What's this? You see a degree symbol? Ah yes, and a graph must be volume of revolution. Whoops. They give you a lot of space, don't they? And rates of change. Alright, so let's start with the first question. This question is a 6-mark geometry question. Figure 1 shows the sector AOB of a circle with center O and radius 8 centimeters. Okay, so this is one circle. A circle of radius 2 centimeters touches the lines OA and OB and the arc AB. Angle AOB is 2 theta radians, where 0 is less than theta is less than pi over 4. So this angle is less than pi over 2. It's acute. Alright, find to 4 significant figures the value of theta. 4 significant figures being a question where they give you the value of theta, as in the angle is theta radians, means you must give your answer in radians. So let's see what we can do. Let's see if there are any lines we can add. So firstly, we know this must be 2 centimeters as well to the center of this circle. And because it's a tangent, it's going to have a 90-degree angle. And we also know that it's 2 centimeters to this point on the bigger circle as well. And because the bigger circle has a radius of 8 centimeters, the rest of the line up until the center of the smaller circle must add with this radius of the smaller circle here to become 8. So this length must be 6. Now we have a triangle, so we'll put C drawing on diagram. Now we have this triangle here, which is going to be very useful to us because we're looking at that radius here. This cuts the angle 2 theta in half, so the angle here is actually just a single theta. So what do we do here? If we have this angle theta and a 90-degree angle here, which is this, where the hypotenuse is 6 and the opposite side is 2, we can find theta using inverse trig functions. So what do we do here? Well, we have the opposite and hypotenuse. If you remember SOHCAHTOA, sine is opposite over hypotenuse, which is 2 over 6, meaning sine theta is equal to 1 over 3, and theta is sine to the negative 1, that is the inverse sine of 1 over 3. And keep in mind that you want to find this answer in radians, right? So sine negative 1 of 1 over 3 gets you 0.3398 radians. So because it's theta radians, your value of theta is going to be just the number 0.3398. So that's your answer to A. You get this by using the inverse sine function on 1/3. Find to 3 significant figures the area of the region shaded in figure 1. Okay, so this should also be quite straightforward. What we're going to do is we're going to find the area of the entire sector, the entire pizza slice, and subtract the area of the small circle inside. So how will we do that? Well, firstly, you might remember or look in the formula booklet to find that the area of a sector is theta, the angle of the sector, r squared, the radius of the sector, over 2 pi. Or, no. My apologies. It's theta r squared over 2. Because, for example, if you have theta equals 2 pi, you just get pi r squared, which is the area of a circle. So the area of the sector is theta r squared over 2. And the area of the circle is pi r squared. Or, substituting in our values, the area of the sector is 0.3398 times 8 squared, because 8 is the radius of the sector in centimeters, over 2. And the area of the circle is pi times 2 squared, because the radius of this circle was 2 centimeters. And now we can perform the subtraction, or we can write out what values we're subtracting even. And after plugging this into your calculators, you should be able to find the answer to this question. That's quite strange. Wait. Hold on. The area of this? Okay, I see what I've done wrong. So, the angle of this sector is 2 theta r squared over 2, because this angle here was 2 theta. My mistake in using theta would only be valid if we were calculating the area of 1/2 of the sector and then adding it to another 1/2 of the sector. But of course this is not the case. This answer set off alarm bells in my head because it was negative. And of course, area cannot be a negative quantity. It's simply against the nature of an area to be negative. So, if you ever notice something like this has gone horribly wrong and something has given you an impossible result, make sure you check your working. Because what you should get, if you disregard the -2, disregarding this, is something more like, because these 2's cancel out, 0.3398 times 8 squared minus 4 pi is equal to 9.1808, which the question was asking us to give to 3 significant figures, so we'll say 9.18 centimeters squared. Okay, now This is actually an interesting thing about my videos, is that sometimes I will make a mistake and then go, oh my goodness, I've just made a mistake, and how do I fix that? I think it is valuable for me to publish that, which is why I don't normally tend to look at the mark schemes beyond getting a general idea of what answer I'm expecting for each question. Like, I'll recognize the number that I get when I see it that it's correct, but I won't look at how to do the question, because I believe it's very valuable to you guys watching this if you can see the gears of problem solving turning in my head, so that it's not just otherwise it's just, you might as well read the mark scheme and you don't get the same insight into the problem solving process that if you were to watch someone struggle with the question, right? Okay, so question 2. Using these identities, show that tan A plus B is tan A plus tan B over 1 minus tan A tan B. Alright, this is quite a satisfying proof. It's actually, I think it's actually how they, it's one way of discerning tan A plus B in the first place, because you can geometrically prove these two and then it goes to this. Alright, so let's take a look at this. Let's label these identities 1, 2, and 3. So by identity 3, tan A plus B is equal to sine A plus B over cosine A plus B. And then by identity 1, sorry, I should have written down what time this question started. It was about 9 minutes 30, I'd say. By the identity number 1, tan A plus B is then, or rather we can put these in one step. By identities 1 and 2, tan A plus B is sine A cos B plus sine B cos A over cos A cos B minus sine A sine B. Alright, so how do we go about this? How do we go about simplifying this to tan A plus tan B? Well, if we want tan A plus tan B on top, the first thing we can do in order to get a tan A of any kind, we can divide both the numerator and the denominator by the same quantity and the fraction will remain the same. So we're going to divide it by cos A, because this sine A, when divided by cos A, will become a tan A, and this cos A will also be cancelled out, as well as cancelling out some terms on the bottom side. You'll get a tan A here, and the cos A here will disappear. So I think we're going in the right track. So multiplying by 1 over cos A, which is 1, we get sine A over cos A cos B plus sine B, because we are cancelling cos A here with the 1 over cos A here, divided by cos B minus sine A over cos A sine B. And what we can do again is, I think the next most obvious step is to divide both the numerator and denominator by cos B again, because what will happen is that this cos B will be cancelled, this cos B will be cancelled to become 1, which is what we want, and this sine B divided by cos B will become a tan B, and as well as this one, which will also become a tan B, and you will get our result here. So multiplying by 1 over cos B, this becomes sine A over cos A plus sine B over cos B divided by 1 minus sine A over cos A sine B over cos b. Sorry about the handwriting being slanted, by the way. The trackpad has been, the tablet's been tilted. And finally, using identity 3 again, we can convert these sines over cos into tans. So tan a plus b is equal to tan a plus tan b over 1 minus tan a tan b. Excellent stuff. Alright, so what are we to do now? Hence show that tan 105 is 1 plus root 3 over 1 minus root 3, and that tan 15 degrees is root 3 minus 1 over 1 plus root 3. Now I'm trying to think what kind of root we would want to take. Tan 105 can be split into multiple different pairs of values, but I think the most obvious one would be just going with 60 and 45, because those are both tan values that we know already. So let's say tan 105 degrees is equal to tan 60 degrees plus 45 degrees. Applying the formula we have worked out, tan 60 plus 45 is tan 60 plus tan 45 over 1 minus tan 45 tan 60. And of course, substituting in values that we already know for the tan function at these special angles, we get is equal to root 3 plus 1 over 1 minus 1 times root 3, which is equal to the form that we want, is 1 plus root 3 over 1 minus root 3. So we have shown BI is true, and now on to BII. How do we do this with tan 15? Well, although we don't explicitly make it so that we are showing how tan a minus b would work, we can still say it's tan a plus a negative number and then work with that negative number. So, for example, in the case of tan 15, our a would be 60 and our b would be minus 45. Tan minus 45 is minus 1. So what would we do? Tan 15 is equal to tan 60 plus minus 45, which is tan 60 plus tan minus 45, tan a plus tan b, divided by 1 minus tan minus 45, tan 60, 1 minus tan a tan b, which is equal to root 3 plus minus 1 over 1 minus 1 multiplied by root 3, which the form we want, root 3 minus 1 over 1 plus root 3, is basically the same as. So this is root 3 minus 1 divided by 1 plus root 3. And notice how in finding tan 15 I chose to use 60 and 45 instead of, for example, 45 and 30. This is because 30 gives us a tan value of 1 over root 3, which is not really that neat, and it would require more manipulation to get from this to this quite simple form over here. It would get you the same answer, but it would not be nearly as fast as choosing 60 and 45 consciously, because they have single term results. In this case, root 3 and minus 1. Alright, let's move on to the next question. This question ended at 1930. Expand 1 plus 3x squared to the power of negative 1/4 in ascending powers of x up to and including the term in x to the power of 6, giving each coefficient as a fraction in x lowest terms. Oh, good lord. Okay. I really dislike that they give only 3 marks for this, especially since it's so computationally intensive. I assume they expect you to use your calculator for this, because it's something that's really tedious and I do not like at all. Anyways, let's see how this goes. So we know that the formula for a binomial expansion of this kind, because we're going up to the term in x to the power of 6, it would be this thing cubed. So we can just use the formula 1 plus x to the n is equal to 1 plus nx plus n minus 1 over 2 squared plus n minus 1 n minus 2 over 6. This is 3 factorial x cubed. Alright, given that our x is 3x squared and our n is negative 1 over 4, we can write this out as 1 minus 1 over 4 times 3x squared plus minus 1 over 4 minus 5 over 4 divided by 2 times 3x squared squared, which would be 9x to the 4. Maybe 9x tetrad. I don't know what the power of 4 is called. Plus minus 1 over 4 times minus 5 over 4 times minus 9 over 4 over 6 times 3x squared cubed. So what do we do here? 1, and then we would just multiply all the numerical parts on one end. So minus 1 over 4 times 3 would give us 1 over 4. Let's just quickly this is minus 3 over 4 x squared. And then what about this? Minus 1 over 4 times minus 5 over 4 times 1 over 2. That's how I'm going to express the fraction in the bottom. Times 3 squared because of the 3x squared squared, which gets us to 45 over 32, positive 45 over 32, and that's times x to the 4th. And finally, this abomination here, so 3 cubed, that's going to be 27 times, and then finally the fractions on top, so minus 1 over 4 times minus 5 over 4 times minus 9 over 4, and then times 1 over 6 for that 6 in the denominator, which gives us 405 over 128. Good lord, these are ugly fractions to work with, but it is okay. And then plus dot 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 as the obligatory measure to indicate that this is an infinite series. Okay, this is our expansion, giving each coefficient fraction in its lowest terms. Yep, find the range of values of x for which your expansion is valid. Okay, so this is a 1-mark question because it is actually quite simple. What you need to do to ensure that your expansion is valid is to make sure that the term that is being added to 1 is of an absolute value less than 1. And because x squared, by its very nature, since we're not dealing with imaginary numbers at all in this course, the absolute value of it needs to be less than 1, but because x squared is positive, we can write this as 3x squared must be less than 1. We're dividing both sides by 3. X squared must be less than 1 over 3. And given that this is a quadratic inequality, we can sort of graph it. Here, it would be a range in between here. X must be less than 1 over root 3, and also greater than negative 1 over root 3. Or if you wanted to rationalize this, negative root 3 over 3 is less than x is less than positive root 3 over 3. So this is the range of values of x for which our expansion is valid. Cool. Find the range of values of x for which expansion is valid. And then now the next part of the question, fx is 3 plus kx squared over 1 plus 3x squared to the power of 4. 1 over 4. Obtain a series expansion for fx in ascending powers of x up to and including the term in x to the 6. Okay, so another way that we can write fx is, because that 1 over 4 is on the denominator, this to the power of positive 1 over 4. This whole denominator term is actually what we expanded in a. So we can write fx out as this numerator times our expansion in a. So this is equal to 3 plus kx squared times by 1 plus 3x squared to the power of negative 1 over 4, or 3 plus kx squared times that series we had, 1 minus 3 over 4x squared plus 45 over 32 x to the 4 plus, minus 405 over 128 x to the 6. And what do we do from here? We only want terms that are x to the 6 or less. So this is going to be equal to 3 times this expansion, because 3 has a term of x to the 0 and it will not affect the exponent at all. Plus kx squared times only the first 3 terms, because if we were to bother multiplying it by x to the 6, it would give us a term that is of a power greater than x to the 6, in fact, x to the 8th. So kx squared times 1 minus 3 over 4 x squared plus 45 over 32 x to the 4 plus dot dot dot. And now we can sum up these terms as neatly as possible. We'll have our first bracket, constant term, plus an x squared term, plus an x to the 4 term, plus an x to the 6th term, plus dot dot dot. And this is how I would like to keep the binomial expansion, as neat as possible. So, what do we do for this constant term? It would be the constant times a constant is the only multiplication that will give us a constant term. So this constant term, 3 times 1, will just be 3. And because this kx squared times the lowest powered term here will still give us an x squared, right? Then we look at the x squared. 3 times minus 3 over 4 x squared will give us minus 9 over 4. And then on this side, k times minus 3 over 4 x squared would give us minus 3 over 4k. Now what? Onto the x to the power of 4 term. 3 times 45 over 32 x to the 4 would give us, let's see, 3 times 45, 135? 135 divided by 32 x to the 4. And this, actually, no, this would be plus k. My apologies, because kx squared times 1 gives us the x squared term. Kx squared times minus 3 over 4 x squared, these two x squareds add up, give us the x to the 4th term. So this would be minus 3 over 4k, x to the 4. And then finally for the x to the 6th term, it's 3 times minus 405 over 128, so minus 1215 divided by 128. And then on this side, kx squared times plus 45 over 32 x to the 4, so it would be plus 45 over 32k. So obtaining a series expansion for fx. Yeah, this is exactly it. We cannot simplify it further than this, simply due to the fact that all of them are in a plus bk form, which is as simple as you can get. No fractions need to be simplified further. Alright, so finally, given that the coefficient of x4 in the series expansion of fx is 0, find the exact value of k. Now, because we've grouped these up so neatly, I am glad we did that. It was a good investment of our time because now this part is trivial. If this is equal to 0, then 135 divided by 32 minus 3 over 4k must be equal to 0, or 135 over 32 equals 3 over 4k. Multiply both sides by 4, we get 135 over 8 is 3k. And finally, dividing both sides by 3, we get 45 over 8 is equal to k. So k is 45 over 8. Excellent. So that is this question done. I'll write that down, 31 minutes in. Into Further Pure and Chill, and they give you this formula book. Differentiate with respect to x, 3x sine 5x. Okay, these are quite methodical questions, and you would be able to use them to do them quickly if you are good at applying the product rule and quotient rule that you have learned. So, let's take a look at this. 3x sine 5x, using the product rule. Let's remind ourselves of the product rule. uv prime is equal to u prime v plus uv prime. So in this case, it's our two things that are multiplied together to get this function. In this case, u is equal to 3x, so u prime is 3, the differential of 3x, and v is equal to sine 5x, and v prime is equal to, let's think for a moment, sine of ax differentiates to a cos ax, because if you let ax be u, and du by dx is that a, then this a will multiply with cos u as part of the chain rule to get this a cos ax. So sine 5x differentiates to 5 cos 5x. Now what do we do? U prime v is equal to 3 sine 5x, and uv prime is equal to 3x times 5 is 15x cos 5x. And we add these up as our final answer, so d dx, meaning the differential of 3x sine 5x, is equal to 3 sine 5x plus 15x cos 5x. Cool. One thing to note, why do I write it like this? Because think of it this way, dy by dx is equal to d dx times y. And instead of y, we're just writing whatever we're differentiating. That's what I mean by d dx bracket this. Next, we have a fraction here, so we can use the quotient rule. This one's harder to memorize, but it is also in the formula booklet. Quotient rule, u over v prime is equal to u prime v minus uv prime over v squared. So what do we do here? Note how this does not say in as simple terms as possible. You can leave the v squared like 4 minus 3x squared brackets squared. So what do we do here? U is equal to e to the power of 2x. U prime is equal to, again, applying the chain rule, e to the u where u is 2x, so we multiply by du by dx, which is 2. U prime is 2 times e to the 2x. v is the denominator of the fraction, 4 minus 3x squared, and v prime, differentiating this, the constant disappears, and minus 3x squared becomes minus 6x. So what do we do here? Let's substitute this all into this larger formula here. U over v prime is equal to u prime v, so 2e to the 2x times 4 minus 3x squared minus uv prime, which is e to the 2x minus 6x, divided by v squared, which would be 4 minus 3x squared squared. And funnily enough, you can leave your answer in this form, because they do not ask you to simplify. So let's just put d dx e to the 2x over 4 minus 3x squared. Let's leave it like this, and we can call it a day. That's literally our answer. Alright, so this question was reasonably straightforward. Now let's move on to question 5. This has a volume of revolutions part, so it must be reasonably computationally heavy. Okay, cos a plus b is cos a cos b minus sin a sin b. Use the above identity to show that 2 sine squared a equals 1 minus cos 2a. Okay, so seeing this cos 2a term makes my mind jump directly to cos a plus a, because that's like the identity that they give us first. That's the identity they intend us to use. So let's try cos a plus a and see where it goes. Cos 2a is equal to cos of a plus a, which is cos a minus sin a sin a. Wow, that's pretty... What can we do here? Well, we can simplify this. It's cos squared a minus sin squared a. But what do we do with this cos squared a? We want a 1 and some sin squared. Well, we can actually use the Pythagorean trig identity, that sin squared theta plus cos squared theta is equal to 1. To substitute 1 minus sin squared a into cos squared a. So cos 2a could in fact be written as 1 minus sin squared a minus sin squared a. Or cos 2a is 1 minus 2 sin squared a. And finally, by adding 2 sin squared a to both sides and taking cos 2a away from both sides, we swap them round as to which side of the equation they're on, and we get the identity we were trying to prove. 2 sin squared a is equal to 1 minus cos 2a. That's excellent. QED, quod erat demonstratum, meaning that we have shown as you have asked. Hence find the value of k such that sin 2a is k 1 minus cos 4a. Damn. Oh, sin squared 2a is k 1 minus cos 4a. We can make this clearer in the sense that if we know that sin squared 2a is k 1 minus cos 2 times 2a, our theta here is like 2a, so this identity still holds perfectly well. And given that if this were to be 2, k would be 1, let's see what we have here. 2 sine squared 2a is 2k 1 minus cos 2a. Now, why did I just multiply by 2? This is because I want to get it similar looking to this identity here. And if this is equal to 1 minus cos 2a by itself, without the k being multiplied to it, this must mean 2k is equal to 1, or k is equal to 1 over 2. So now what do they expect us to do? Figure 2 shows part of the curve with the equation y is equal to 3 sine 2x. The region R bounded by the curve, let's just write this down, 3 sine 2x. The region R bounded by the curve, the positive x-axis, and the line x is pi over 6 is rotated through 360 degrees about the x-axis. Use calculus to find to 3 significant figures the volume of the solid generated. Alright. We have our volume of revolution formula equipped to help us. V is pi integral from point 1 to point 2 of y squared dx. Let's see what we can do. Given that y is equal to 3 sine 2x, and that we are approaching this with the bounds given in the question from 0 to pi over 6, and y squared is 9 sine squared 2x. V is equal to pi times the integral from 0 to pi over 6 of 9 sine squared 2x dx. And hold on a minute, we've just figured out a formula for sine squared 2x anyway. It's a half times 1 minus cos 4x. So let's apply this knowledge. First, I want to move the 9 outside the integral to make it neater. So it's 9 pi, 0 to pi over 6. Or in fact, let's make this 9 pi over 2, 0 to pi over 6 of 2 sine squared 2x dx. And the reason why I am moving 9 over 2 out is so if we leave the 2 in here, we can get this much neater form of 1 minus cos 4x instead of 1 over 2 minus 1 over 2 cos 4x. I don't know, it's just a personal preference. It looks nicer when you are evaluating it. So this is equal to 9 pi over 2. By our findings from A and B, this is equal to 9 pi over 2 of 1 minus cos 4x dx, or 9 pi over 2, the definite integral over the bounds x, and then minus cos 4x. Well, let's look at our axes again. If this is cos, sine, minus cos, minus sine, and differentiation is this way, integration must be this way, so minus cos goes to minus sine. And by the reverse chain rule, we get x minus 1 over 4 sine 4x from 0 to pi over 6. Now what do we do? This is 9 pi over 2 of, firstly, let's evaluate it when it's pi over 6. So pi over 6 minus 1 over 4. What's sine 4 times pi over 6? This is 2 pi over 3. Let's check our unit circle again. We're going from 0 to pi 2/3 of the way. And this is when there's about 30 degrees here. So this would be root 3 over 2 is the sine value for 2 pi over 3. Minus, and then 0 minus 1 over 4 times 0, which is sine 0. So that's all 0, we can ignore it. 9 pi over 2 times pi over 6 minus Hold on a minute. Oh, no, yeah. Okay, my apologies, I panicked. This should be root 3 over 2. I accidentally wrote the angle instead of the sine of the angle in there. So, pi over 6 minus root 3 over 8. And now we multiply the brackets out to get our final answer for volume, which is going to be 9 over 18, that's 1 over 2, so 1 over 2 pi squared minus 9 over 16, 9 root 3 pi over 16. You can't really simplify it more than that, so this is our final answer. And no. Let's go back to the question. Find to 3 significant figures. We're not finding the exact value. So, what we can do here, we stick this into the calculator. Pi squared over 2 minus 9 root 3 over 16 pi gets us 1.87401 or 1.87 to 3 significant figures. Now let's just quickly check if there are any units involved. No, I don't think so. So 1.87 units cubed. That's our final answer for the volume. Alright, that went pretty successfully. Now we're moving on to question 6 at 47 minutes and 18 seconds in. A solid paperweight in the shape of a cuboid has volume 15 centimeters cubed. The paperweight has a rectangular base of length 5x. Let's draw this out. The paperweight has a rectangular base of length 5x and width x and height h. The total surface area of the paperweight is a centimeters. Show that a is 10x squared plus 36 over x. Alright, so if we were to calculate a using just the lengths we've been given, it would be kind of whack because h would be present in the expression and we want to get rid of h if they're only asking us in terms of x. So we need another equation that relates h to x, and that is helpfully found in the equation for volume. Just going to get some water. Okay. So this volume 15 is going to be equal to the width times length times height, or 15 is equal to 5x times h, the height. So what do we do here? 15 is 5x squared h, or h is 15 over 5x squared, which is 3 over x squared. That is our value of h. And we can use that value of h in terms of x, substituting into our expression for area in terms of x and h to find an area in terms of x only. So the area is going to be 2 times the area of each of the 3 unique faces. So it will be 2 times 5x times x plus 2 times x times h plus 2 times 5x times h. And what do we do here? This would be 10x squared plus 2xh plus 2 times 5x times h plus 12xh and substituting in that h is 3 over x squared, a is equal to 10x squared plus 36x over x squared, which is 10x squared plus 36 over x. And that is how we would show that the area is 10x squared plus 36 over x. Because remember, they have given us another equation to find h in terms of x by telling us the volume. This is a similar pattern that's repeated through many of these related rates problems. Find to 3 significant figures the value of x for which a is a minimum, justifying that the value of x gives a minimum value of a. So, to justify something, we'll deal with that later, but you need to use the second derivative. So let's find the first derivative. dA by dx is 20x minus 36 over x squared. By using the power rule, 36 to the negative 1 goes to minus 1 times 36 to the negative 2. That's what I've just done in my head, 36x to the negative 2. So dA over dx is this, and we want to find the value of x for which a is a minimum. So min or max at dA over dx is equal to 0. 0 is equal to 20x, 0 is equal to 20x minus 36 over x squared. 36 over x squared is equal to 20x, or 36 is 20x cubed, multiplying both sides by x squared. 9 over 5, because we divided both sides by 20, and 36 over 20 simplifies to this. 9 over 5 is equal to x cubed, and x is equal to root 9 over 5. A cube root of 9 over 5, sorry. Now we must justify that dA by dx, that this is a minimum. Justification? Think of it this way. How do you justify that something is a minimum or a maximum? When you're looking at a maximum on a graph, the gradient here is 0, the gradient here is negative, and the gradient here is positive. And then the minimum is the other way around. It goes negative, 0, positive. So if we graph the second differential, if we graph the first derivative, if this is the minimum with our vertical line through it, it would be positive, and then 0, and then negative. And for our minimum, it would be negative, and then 0, and then positive. And the important thing, to show that it goes from negative to being positive through this 0, we need to show that the gradient here is positive for it to be a minimum. It's the rate of change of the rate of change. So for a to be a minimum, d squared a over dx squared must be greater than 0. How do we justify this? Well, d by dx of dA by dx, to get our second differential, which was d by dx of 20x minus 36 over x squared. Let's rewrite 36 over x squared in a power form to make it clearer what we're doing. Is d by dx 20. This is in its entirety going to be 20 because 20x differentiated is 20, and then plus minus 36 times minus 2 times x to the power of negative 3 by the power rule, because this minus 2 is brought down. So 20 plus minus 36 times minus 2, 20 plus 72 x to the power of negative 3. And when x is the cube root of 9 over 5, as was found here, d squared a over dx squared is equal to 20 plus 72 over 9 over 5, which is equal to 20 plus 40, which is 60, which is greater than 0. Therefore, a is at a minimum. QED, quad irrat demonstrat. We have demonstrated that it's at a minimum. So now, finally, we must find the three significant figures and the minimum value of a. What we do is we plug in this value of x back into our original function for a. So for c, if ax is 10x squared minus or plus 36 over x, a of the cube root of 9 over 5, the minimum, in fact, is a of the cube root of 9 over 5, which is 10 times 9 over 5 to the power of 2/3, plus 36 times 9 over 5 to the power of 1/3, negative 1/3 because it's over x. We can, again, put this into the calculator and it will give us a numerical answer. Let's see how it goes. 10 times 9 over 5 to the power of 2/3 plus 36 times 9 over 5 to the power of negative 1/3 is equal to 44.3918 ... which is 44.4, and given that the surface area is a cm squared, a is not a quantity with units. We can put the box around here and in brackets cm squared. 44.4 cm squared is our final answer to three significant figures. Alright. So I hope this video was helpful to you if you watched it. I hope I have satisfied the wish of the commenter in my previous video to do the first half of this paper. So again, if you're watching this, I hope you found it helpful. And if you have any corrections to be made to this video, or videos you would like me to make conceptually, not just as selections of past paper questions, then feel free to leave a comment and I will follow up on your request. Thank you very much for watching.